Hello, there he is. There he is. There she is. There they are. There she is. There they are. There's the complex. Wow. Okay. I don't even. Hello, hello. Wow. That's all of. Okay. Hello, Chris. Hello, Cheska. Hello, Avani. Hello, how you? Hello, Amanda. Okay. Okay. This is so. I feel like this is physics. Okay. And hello, hi you. Wait, did I just say? Oh, hello, hi you. Oh, hi you gave me. I mean, good afternoon, hi you. Sorry. Yes. Okay. Good afternoon. Hold on. Who else is it? Good afternoon, Michelle Q. All right. Good afternoon, Melita. Good afternoon, Michelle Q. Good afternoon, Marilyn C. Good afternoon, Matthew. Good afternoon. Oh my God. We're like so close to 100%. There's Michelle F. We are so close to 100. Oh my God. I have to open up a portal. This is, and if we count Michelle, oh my God, there's Melita. And if we count Michelle Q as like almost video, hello, Melita. Guys, I've never been this close. I'm just saying. Oh, and sorry. Good afternoon, Amanda. Oh, I did say good afternoon, Amanda. Okay. Good afternoon, everybody. Okay, guys. I mean, I guess you're probably waiting till you get your exams back. That's fair. But if this class can pull off 100%, I mean, and then it's gonna pull off 100% attendance at 8 a.m. physically next semester. What? And 100% Dunkin' Donuts attendance. What? Okay. And now there's been attendance in my office, which I'm so happy about. I really appreciate people that are visiting me in my office. I know I should spend more time there, and I'll try in the future. I know the hours are not very convenient, but it is very nice to be meeting some of you people in real life these days. Okay. Oh, wait, the person who made it. Oh, wait. Okay. Okay. Don't get me distracted. Oh my God, the Chris thing in the chat. I actually know. Don't. Oh my God. Now I'm not gonna be able to do physics at all with that. Don't tell me, don't give away the answer, Chris. Don't. I mean, it's gonna be bothering me. Wait, I know it's not a coffin, but it's something like that. Wait. And it's not a lap. There's also something like that, like when you stand up, it disappears. When you sit down, okay, don't tell me. Don't tell me. Put a portal. We'll make a portal out of that. All right. But don't tell me seriously. I kind of love to hate questions like that, or I hate to love. Anyway, all right. Whoa, and there's Yayun. Hello, hello. Wow. All right. I'm gonna stop talking because I know we have to do physics, but I'm gonna miss this class when they all abandon me at 8 in the morning next semester. No, I'm not. Okay, yeah, let's just get going. Okay. But yes, I really enjoy you people. I'll just leave it at that. And the exams are still just coming in. I don't have anything to say about them. You're being very patient. I appreciate it. You'll get them, each of you, when you get it. Excuse me. All right, what we have to do today, it's a little bit fun. I know that many people in both sections like have questions about homework. Oh, there's Yavi. I thought Yavi was here. Wait, didn't we already say hello to Yavi? Okay, whatever. I mean, homework 8 is what I want to be going over. We will get to some of homework 8 today. Many of you have made a really solid attempt and turned it in. Some of you still have to, of course, the other people are very concerned about this. It's still the case, folks. If I start going over, if I'm doing anything in this class and you start to realize, oh, now I see how to do things in homework 8 that I was doing wrong or something like that. If you can definitely correct and re-upload for sure. Always, always, even the old homeworks. You can always re-upload for higher numbers. Like that's the point. That's the point. And especially if you suddenly have a moment, because this was happening this morning to other people, if you have a moment where you're like, oh, if I had understood this when I tried the homework before, then blah, 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 that's all good. Like if you want to correct for more points, you can, or if you don't care about the points, you don't have to. But if you ever have the feeling like, wait, I tried this already, now I get it. I wish I had gotten this when I tried it. No, you got to understand that's the trade-off is if you're having that feeling because you tried the homework before we were talking about it, as we ask you to do, that actually means you're getting much more out of the lecture than you otherwise would have. Like, I won't dwell on it, but it's really a good thing when you hear something in lecture and you're like, oh, now I get it. That means it's all working, really. That's why you try things. But anyway, you get my point. So you can always just keep turning in things for more points. Always. I work because yes, the duck's place is good. And I don't even think, was it this class? Yes, I know there's a big theme of ducks in this class. We have a lot of ducks. It's not even because I love, anyway, we already talked about that. It's a coincidence, sort of, but now I love ducks, I guess, for the rest of my life. He works a 9 to 5. That's funny. All right, I'm just kidding. So what we're doing now, what we have to do, I'm going to turn the page of the notes. What we're here to do is finish. Okay, that story I need to hear someday. I don't even know what that, how do you steal a duck? I didn't even know anybody owned it. Okay, don't do this to me. Okay, I'm going to go to the notes. What we've been doing is, I know that like about 3 classes ago, I introduced this sample example problem that we've been doing in class. I want to finish it before I go into homework 8. The point is that this sample problem is sort of elaborate. It deliberately has almost every element that could ever be in any of these homework problems or exam problems or the lab problems. Like all the elements are together in a way in this sample problem. So if you can follow through the whole sample problem with me, then it is the sample of all samples. So we're going to finish it and then go to homework 8. And you'll find that some of the things in homework 8 are comparatively, they'll seem easier now compared to the sample problem, hopefully. So where we were with the sample problem, I believe, just to remind you, we had this sled. I keep saying sample problem because I don't want to confuse anybody into thinking you can't find this in any of the homework sheets or anything like that. It was just made up in class or presented in class. Okay, anyway, we've got the sled on a rough ground. The sled is being pulled by some string at some angle theta. Therefore, the sled is accelerating horizontally along the ground. Just that it's accelerating horizontally along the ground, and the magnitude of that acceleration is what we're ultimately, what just happened? Sorry. The magnitude of that acceleration is what we're ultimately trying to figure out. And in this sample problem, like, notice I didn't even give you any numbers. We're really sort of getting into more and more physics here. I'm just giving you constant letters to stand for the values of things that would be known in a problem like this. So our ultimate answer that we're going to get, is going to be a function. When I say that we're going to get an answer for A, it won't be a number. It'll be some expression, some function of m, theta, mu, and g. And it won't necessarily be a simple or neat or elegant expression. It'll just be an expression of those knowns. Then if we have values for those knowns, we could set them and plug in and get a numerical answer for A. But that's what the goal is here. And let's even be more specific, because in this class, I know I had a chance the other day to with you guys, I had a chance to sort of lay out the fact that there's 2 different types of friction, really, right? There's kinetic friction and there's static friction, and they never operate at the same time. Generally, static friction tries to hold something in place for a while, and then when static friction fails, then a surface will slide along another surface, and kinetic friction will kick in and remain constant for the duration of the motion. So the reality is that most surfaces are identified by 2 different coefficients of friction, one for the static case and one for the kinetic case. So to be really more proper here, I should say that in the 2 givens in this problem, I mean that there's 2 given coefficients of friction in this problem, one for when things are being held together and one for when they're moving. In this problem, the entire time the sled is moving. So we're only really going to be concerned with one of the coefficients of friction, but in general, just understand that surfaces are identified by 2 coefficients, the coefficient of static friction and the coefficient of kinetic friction. All right, so this was the situation, right? And our goal is to compute A. I'm doing this to lay out the procedure that works for all Newton's law problems. The procedure was we first created a system schema in order to identify what all the forces were that are acting on this thing, to find out how many forces are acting and what they are. Then from the system schema, we take every single line out of the system schema and we turn it into a vector arrow in a pure free body diagram. So we went from system schema to identify the forces to pure free body diagram to identify the directions and the comparative magnitudes of those forces. And then what we're supposed to do is go from there to a component free body diagram. And that's the stage essentially where we left off yesterday. Like this was our situation. And the last place we left off, I mean, not yesterday, Monday, was we had a pure free body diagram of the sled on the ground. The pure free body diagram, I believe, looked like this. These were the four forces that were acting on the sled. I'm just gonna, and now what the whole idea of all of this is that we want to use F net equals ma. We want to apply Newton's second law to compute the acceleration. All of the purpose of all these diagrams were to get all the F's that have to be plugged into the left side of F net equals ma, the F net side. And we're almost ready to do that. But the whole idea, we're almost ready to do that, but we're not quite there, because the whole idea is that F net equals ma is a vector equation. Excuse me. F net equals ma is a vector equation. Okay. F net equals ma is a vector equation, which really means that it itself is a set of simultaneous yet independent equations. F net equals ma really means, as it says at the bottom here, it really means the sum of all of the x-axis forces produce the acceleration of the mass along the x-axis, while at the same time, but utterly independently, the sum of all of the y forces produce the acceleration of the mass along the y-axis. So this picture is not yet ready to use, because we need a picture in which every single force is lying along a coordinate axis, like x or y, or z also, if there were a z-axis. So what we have to do is choose a coordinate system and resolve those vectors into, we have to break up any vectors that are not lying strictly along an axis. We have to break up into components that lie along axes. That's what this says. So we've got to zoom in on any force which does not lie along an axis and resolve that vector into components, just like we did with velocities in the free float problem and what we did with displacements and so forth. Okay, but in order to do this, in order to divide forces up into components that lie along axes, we have to know what our axes are. This is all Galileo. The laws of physics will work in any coordinate system, any unaccelerated coordinate system. So we have to pick a coordinate system that will be as convenient as possible. So the strategy, what it says in the bottom on the brown, I mean, what it says on the bottom in the brown, it says strategy. The strategy always going forward with any Newton's law problems is we choose an x-axis that we choose to line up our x-axis with the line, the direction of expected acceleration. That's the strategy. So this is a strategy that's meant to encompass inclined planes, like from the lab, or like pendulums, like you're going to focus a lot on at the beginning of Physics 204. Like no matter how an object might be accelerating, maybe accelerating on a slant, or maybe accelerating along the radius of a circle, no matter how an object is accelerating, we line up our x-axis with that, and then make our y-axis perpendicular to the line of acceleration. Now, in this case, it's not so. In this case, it almost seems unnecessary for me to say that. In this case, we expect that the sled is accelerating purely horizontally, like purely along the ground. So I'm going to call that my x-axis. Now, often that's what you call the x-axis, but I'm just trying to say that's not, the x-axes are not always horizontal. In this case, I think we will make the x-axis horizontal because that is what the acceleration is doing. Let me also emphasize again, one of the reasons I'm making a big point of this is, the sled is being pulled up at an angle. The string is pulling up the sled at an angle, but that does not mean that the sled is flying up at an angle, right? The assumption, the belief of this problem is that the string is pulling up an angle for reasons having to do with leverage or just the height of the child pulling the sled or whatever. They're pulling it up on an angle, but the sled is somehow nonetheless sliding along purely horizontally. So that direction is what I'm calling, that direction of purely horizontal acceleration is what I'm going to call positive x. And therefore, the line perpendicular to that going up, I'm calling positive y. Okay, so that's like my lens. That's my coordinate axis, my perspective through which, or like my transparent graph paper through which I'm analyzing the sled. Therefore, if that's my lens, if that's my coordinate axis, if you look back at the pure free body diagram, you see that the one and only force that is not lying along the x-axis nor the y-axis is T, the tension. So in this case, because of the way we chose our axes, T must be resolved, must be broken up into two vector components, like we did with velocities and displacements and all that. So we zoom in on T at the bottom, like we look at T, it must be resolved. So we zoom in on it, just like we did with velocities and displacements. And the angle at which T is pointing is that angle measured from the horizontal. So to pull up and to the right is equivalent to pulling some extent right, and while simultaneously but independently pulling some extent up. What extent right? Some percentage of T. What percentage? Cosine of theta. That's a percentage, right? Cosine of an angle is always some fraction, some decimal, some percentage. And we're also pulling up. What percentage? I mean, what amount up is the string pulling? Some percentage of T. What percentage? The sine theta percentage, right? So that's what those two components mean. We draw them tip to tail. I literally believe that to pull up and to the right is equivalent to pulling some extent to the right plus some extent up. So that tension is equal to the sum of those two components. That means I'm now going to make a substitution. It means that in my pure, and this is something people often do wrong on final exams and stuff. Like we don't add, basically notice this. I made a separate picture. I zoomed in on the T separately outside of my pure free body diagram. I analyzed it. I got two components. Now I'm going to go back into my diagram. And the purpose of doing this is I'm going to substitute those two components for the original hypotenuse that's sitting there in a diagram. Basically, I'm saying as a pro tip, if you're doing this on an exam, don't do what I just did in the middle of your diagram. Leave your diagram alone, make a separate diagram for this. And now from this, we create a final diagram, which is called the component free body diagram. If we're doing this all correctly, and of course, it always takes me longer to talk about it than for any of you to do it, but it is a process. You start with a system schema, you go to the pure free body diagram from that, and from the pure free body diagram, you break up whatever vectors need to be broken up, and you finally create a component free body diagram. Here is this is the final diagram. And finally, it's setting us up to do the math. The math is the easy part if you've done all this correctly. It takes care of itself, basically, the math. I should never say easy, but I mean, it's much clearer than it would be if we didn't do all these diagrams. So this is my component free body diagram. Notice T is not in this diagram. T is gone. I got rid of it because I substituted in for it T sine theta and T cosine theta. I'm saying together they're doing the job of T. You again, pro tip, like classic error that people make on the exams is, especially if they try to cram all this into one picture, they'll often add T sine theta and T cosine theta to their original diagram. So then they'll have T sine theta, T cosine theta, and T. That's like deeply wrong. It like always annoys people when I take off points for that, but that is deeply misguided. That like literally, if you take all this stuff seriously, you're then going to double count the tension. You're going to count the tension twice in all of the equation. Anyway, so don't do that. So we now have a diagram where every force is either pointing along the y-axis or it's pointing along the x-axis. And every force that's pointing along an axis is either pointing in a positive direction or a negative direction. So now finally we have something to work with here. Now it's just like addition and subtract. Well, now it's just addition, really, in its simplest form. Sorry, I don't know why that line. Sorry, there's like a. It says at the bottom, if arrows are meant to be equal in length, put hatch marks. Okay, the reason I wrote that. Wait, sorry, but so this diagram now has a total of 5 arrows in it. That's like not simple. I mean, could situations get more complicated than that? Yeah, but they usually don't get much more complicated than that. This is about as thick as a situation can get. That's why we're doing it all like over a series of days. Oh, but I wrote at the bottom, I just want to make clear because a couple of really good questions were asked about this in the other section. Like the arrows are meant to show direction. They're also meant somewhat approximately to show magnitude. We can't show exact magnitude with the lengths of these arrows because exact magnitude is what we're doing computations to figure out. We don't know exactly how big anything is until we're done with the problem. But we have a sense when we draw this diagram of what things, or we should have a sense of what things are going to be bigger than what forces are going to be bigger, stronger than which forces. And most particularly, we should have a sense of whether any particular forces are equal or not. If you believe that two forces, if you have good, active, specific, conscious reason to believe that two forces in the diagram should be equal to each other in strength, then you make the two arrows equal in length, sure. And traditionally, if you thought two things were equal, you'd put like hatch marks to really signify, to really emphasize that, just like a little mark in each one of the arrows. I want you to notice that that is not the case here. I may be being rough and approximate in the lengths of these arrows, but what I'm trying to get across really is that I don't think I have no reason to believe that any of these arrows are equal to each other. I'm trying to combat that preconception with this exaggerated diagram. There's at least one person in the other class who had the sort of honesty to admit they were surprised. They would have assumed that my N up arrow should be equal to my down MG arrow. A lot of people think that a lot of the time. In fact, there's a lot of websites and a lot of textbooks that they're not wrong, but if you kind of don't read them extremely carefully, they can give the impression of that the normal force is often equal to the gravitational force. It's not. And sometimes it is, but I'm just trying to say there's no reason to assume that the normal force arrow is equal to the mg arrow, or that the normal force arrow is equal to the T sine theta arrow, or for that matter, let's go to okay, I'm going to move on in a second, but notice I definitely did not make the T cosine theta arrow equal to the F arrow. Like I definitely did not make those equal. Why not? Well, because the whole premise of the problem is that this thing is accelerating to the right. We're trying to calculate the acceleration to the right. If the two horizontal forces were equal to each other, there would be no acceleration to the right, right? It must be the case, if this thing is accelerating to the right, that there's a net, like the whole purpose of F net equals ma is that there must be a net force acting on this sled, a net force pulling pulling to the right. T cosine theta has got to be bigger than F if the thing is accelerating in the direction of T cosine theta, right? That's what I'm saying. I'm not saying T cosine theta could never be equal to F, but I'm saying if it were, then that would mean A equals 0. That wouldn't necessarily mean the thing isn't moving, but it would mean that it wasn't accelerating. Last thing I want to say about equal and opposite, you're going to see in the duck problem that we're after Chris returns it, in the duck problem that we'll go over after this, you'll see it starts getting involved in asking you questions about Newton's third law. There's a reason for that. I want to emphasize like well, you'll see when we go over it, T cosine theta and F are opposite. They are opposite. Just because two things are opposite doesn't mean they're equal. And furthermore, as you'll see in the next problem, just because two things are equal and opposite doesn't mean they're an example of Newton's third law. Newton's third law does not say that there have to be any equal and opposite forces in a given free body diagram. In fact, quite the reverse. Well, we'll get to it in a minute, but please don't, you should take Newton's third law seriously, but don't think it means that for every rightward pointing arrow you have in a diagram, you must also have a leftward one. Not at all. Just so you know. All right, so we'll get to that. All right, anyway. So this is the diagram. This is the component free body diagram. Now we can finally do the math. What math do? We do Newton's second law. F net equals ma, vector equation. So we're going to apply it to one axis, then we're going to apply it to the other axis. Strategy. Here's so that's true. We're going to apply it once to one axis and then independently to the other axis. So you in theory could do in any order you want. You could choose any axis first you want. But pro tip, was it this class that said about pro tips? I think it, right? I think the whole concept of pro tip started in it. Oh no, it started in that. Anyway, pro tip for exams. Gonna open up a portal for pro tip. Anyway, pro tip is, because the acceleration that I'm solving for is pointing along the x-axis, and it generally will be because I strategically generally set up my x-axis exactly to lie along the line of acceleration. So generally speaking, the answer I'm looking for lies on the x-axis if I'm doing things strategically. Therefore, my strategy is I'm always going to start by analyzing the y-axis. I am always strategically going to leave the axis of ultimate interest for ultimate last. Because if the other axis is giving me any information at all, I'm going to need that. If it's worthwhile information, I'm going to need that information for the final calculation I do on x-axis. So I try to get any information I can first from the y-axis and then use it on the x-axis. You'll see what I mean right here. So I'm going to start with the y-axis. I do F net equals ma on the y-axis. So my job is now to expand out the left side. All of this work that we've been doing for a week is all to know what to put in for that left side. The left side says the sum of all of the vertical forces pointing in the directions that they're pointing in. That's what I would never, ever know what they are unless I had done all these pictures. I look at the picture. I look at my component free body diagram, which is all I need at this point, but I couldn't have made it without the pure, and I couldn't have made the pure without the system schema. I look at the component free body diagram. I look at that y-axis, and I see a total of 3 arrows on it, 3 forces. So I'm going to write down 3 forces on the left side of F net equals ma. I'm going to add them all up, like sum of the net force means add up all the forces. So I'm going to add up those 3 magnitudes that I'm reading off the chart, off the diagram from the y-axis. I'm going to add them, but 2 of them are going in one direction, in the same direction as each other, and the other one is going in the down direction, the direction that we call negative. So I'm going to add them all up, but I'm going to put a minus sign on the down one. This is how I always do it. Okay, you're just adding up all the forces going one direction minus the ones going in the other. So I'm literally going to write T, no, I'm not. I'm literally going to write N plus T sine theta minus mg. That is the net force in the vertical axis. So N plus T sine theta minus mg equals ma. Equals ma. sub y, like the acceleration along the y-axis. That is my F net equals ma statement for that axis. But now, what am I like? Why do I care about the y-axis? Again, my ultimate concern is the x-axis. Why am I even like diddling around with the y-axis? Because, well, for the because of the following. With the x-axis, we're using information about forces in order to get acceleration. That's like always ultimately what we're doing. We're using information about forces to get the value of acceleration. But on the y-axis, we already know the acceleration, whether we think we know it or not. We already know the acceleration along the y-axis. In fact, that's another reason I'm focusing on the y-axis right now. We know the acceleration on the y-axis, so we can use it to get information about the forces on the y-axis. What is the acceleration on the y-axis that I'm claiming we already know? It's 0. Because on the y-axis, the sled is not the sled is not flying up into the air and it's not crashing through the ground, right? We set up our axes on purpose so that we've got this one axis where nothing is happening at all. Well, no acceleration is happening. I'm not saying that there aren't pulls or pushes. There's 3 pulls and pushes, but somehow they're balanced on the y-axis. Right? On the y-axis, the acceleration is definitively, by hypothesis of the problem, 0. So I can substitute in 0 for that a sub y, and I can say, and I therefore, so the whole left side equals 0. Therefore, I can bring the mg to the right side, and I realize something. Okay, n plus t sine theta equals mg. That's why I drew the arrows that way. Like, if you really think about it, so the sled has weight, mg. The floor is pushing up, trying to support that weight. Yes, the normal force from the floor is pushing up, trying to support that weight. But there's also this string on the sled pulling up, right? So the string and the floor are helping each other support the weight of that object. The floor doesn't have to push up as hard as it typically would if there weren't a string there. If there weren't a string there and nothing else was going on, then the normal force would presumably just exactly support the weight, which is why sometimes some people think N equals mg. Sometimes it does. But that's not like a law or a formula or anything. The normal force just does what the normal force needs to do in order to obey the law F net equals ma. Wait, someone raising their hand? Does that mean if you're raising your hand? Wait, sorry. Wait, is someone raising their hand? I'm sorry. Hold on. If someone's raising your hand, wait, I can't see, but definitely ask a question. If someone has a question,
You're raising your own hand, Professor.
Oh, of course yes. Okay, thank you. Yes. Well, I don't know why that. Okay. Oh, because I'm yelling so. Okay, that's so funny. All right. Thank you. I've taken spastic gesticulations to a new level. How am I? Just because the volume of my voice is right? All right, anyway, it doesn't matter, but wait, that is funny though. And thank you, Avani, for the Bitmoji. I mean, but wait, is that just because I'm yelling? Or is it because it sees me going like this? Wait, right, I totally can. But I do have good Bitmojis, you have to admit. Wait, I totally do. Wait, I honestly would like to. Okay, all right, I don't want to go into, but that is really, that happens all the time. I never realized that was me. Okay, stop. How many ADHD physics professors does it take to screw in a light bulb? A fish. Okay. You know that joke. Okay, all right. See, I totally. See, by the way, okay, I'm going to admit this. You understand what the real lesson of this whole class is? The whole purpose of why you're taking this class is just to send a constant subliminal message. If I can make it in life, if I can get through science and get a job, you certainly can. You know what I'm saying? Right? Like somehow it works out. Okay. I mean, somehow. But okay. I do forget. Okay. So on this diagram, it's showing that the normal force upward from the floor is working with the upward pull of the string to exactly support the weight of that sled. So that's why actually, if you really look at my arrows, what I was roughly trying to do is make it so that the length of the N arrow plus the length of the T sine arrow roughly speaking, equal together the whole length of the mg arrow. Now, that's because like I knew where the problem was going. You might not always, and I didn't do it that exactly, but that's the concept that's going on here. And the real thing I'm trying to say is, you see, the normal force just does what the normal force needs to do. The normal, and you'll see that in the next problem with the duck in the elevator too. The normal force is not something you can know in advance what it's doing. It picks up the leftovers and fills in the gaps of whatever else is going on along that axis. Okay, so anyway, where'd it go? Sorry. So okay, so n plus t sine theta together are supporting the weight of the object. Therefore, I can bring t sine theta to the other side and say and conclude finally the normal force equals mg minus t sine theta. That is a way of saying, again, the floor is pushing up as hard as it can to support the weight, but minus, but less so by whatever amount the string is contributing. So the normal force supports the weight minus whatever the string is doing. Now, why do I care? Like, okay, that's all very interesting. Partly I'm saying that to reinforce that you got to think about the normal force carefully on its own, always. But there's a specific reason I care about the normal force, and there's a specific reason that I looked at the y-axis first. And that is that if I now turn my attention to the x-axis, where I'm really concerned, if I look at the x-axis in order to find out how fast this thing is accelerating along the x-axis, friction is going to get involved now. And friction, right? I mean, if I look at the diagram and look at all the arrows on the x-axis, I've got t cosine theta going to the right minus friction going to the left. Together, they equal ma along that axis, ma sub x, right? So we're getting somewhere, but now we've got, it's what that says in my horrible handwriting. It says, how do we compute F being friction? Like, we've got to expand F in terms of known quantities. Well, we said 2 days ago that the friction force arises from two factors: the roughness of the surfaces, which we call mu, and how hard the two surfaces are pressing against each other, which we call the normal force. So, right? And so the product of those two factors together make the friction force. That's the general thing for friction. We said specifically yesterday, now this says specifically here, the sled is sliding when one surface is in motion relative to another. The case is known as kinetic friction. I'm just reminding you of what we said 2 days ago, that there's really two cases of friction, right? There's the kinetic sliding case, but there's also the static sitting still case. Here today in this problem, we were told from the start that the sled was being pulled along the rough ground, and it was in fact sliding. So we are talking about kinetic friction here. In this particular problem, we're not worried about the subtleties of static friction. I'm just like reminding you of the fact that in principle, every surface has two different coefficients, mu sub k and mu sub s. Here, we're concerned with mu sub k. So really what we're saying here is F sub k equals mu sub k times the normal. So we plug that in. Right, I'm saying, okay, so that was just a summary. I'm saying here, the friction force, kinetic friction force, is mu sub k times the normal. So we plug that into the x-axis Newton's second law statement. We now have t cosine theta minus mu k times the normal equals ma. And this is the reason we did all that computation on the y-axis. Like, directly speaking, I wouldn't care about the y-axis, but the y-axis is what gave us the information, the expansion of the normal force magnitude. That was the purpose of it. So we plug in that expression that we got. We got that n equals mg minus t sine theta. So we plug that in for n. That was why we went to the y-axis. And so now we have a complicated expression. Again, I'm on purpose. I mean, it's weird. Like, I'm on purpose, especially because you've already been in lab and stuff like that. I'm just giving you sort of a super complicated, a comparatively complicated problem so that you could just see all the details of this at once. So we now have this complicated expression, t cosine theta minus mu times mg minus t sine theta equals ma. And we're looking for A. That's been our goal the whole time, looking for A. So we divide both sides by M, and we get this really long thing. A equals T cosine theta minus mu mg plus mu times T sine theta all over M. That's pretty complicated. Given the situation as we know it, I can't really make that much simpler or much neater or much prettier. That is technically the answer. The acceleration in this situation, when you have all these forces happening and some of them happening at angles, the acceleration of the sled expressed as a function of given constants would be that. I mean, that technically is the answer that we're looking for, and we'd be done. But it's like so messy and everything that just to sort of put this in perspective or make it more concrete, let's imagine that we had numbers, we had numerical values for these constants, like say theta was 30 degrees, say the mass was 2 kilograms, say mu sub k was 0.2, and say that the tension in the string was like 25 newtons. And notice, by the way, notice these units are careful, like mass is measured in kilograms, tension is a force, it's measured in newtons, mu is not a force, it's a coefficient. It's just an index, a number that a ratio of forces that represents roughness. So mu is just literally the number 0.2. Please do note that. That's not a typo. Mu is just the number 0.2. And theta is 30 degrees or pi over 6 radians. And so then if we had those numbers, we would plug into that expression, right? So we just plug straight in. Oh, and someone asked about this in the other class too. So I'm just plugging in. And I would get an answer at the end of the day. My answer is like approximately 20.2 meters per second squared, which is pretty fast, but it's not ludicrously fast. I mean, it's pretty fast. It means you're pulling pretty hard. I mean, that tension was on purpose a pretty high number just to get this thing going. One thing though, that someone asked in the other class, if you see that 10 that I put in there, like when I plug the numbers, I have A equals 25 cosine 30 minus 0.2 times 2 times 10. If you're what is that 10? That 10 is G. Like whenever we write mg is the weight, right? mg, which is the weight of the object, and G, by G we always mean that, oh, here comes Felix, that free fall acceleration number, approximately 9.8 meters per second squared. But as long as we're not in lab and as long as you're not told otherwise, we can always approximate that 9.8 to be 10 meters per second squared. So that's where that 10 came from. But, and now that I'm saying that too, I should also highlight something they didn't ask in the other class. It just occurred to me. Notice the way I'm doing these problems, and it's not the only way, but it's definitely the way that works best for me. And I think I highly recommend this way of doing it. Notice the way I'm doing it. We're taking the vector arrows so seriously. We're taking the diagram so seriously that we're using the vector arrows to show direction. Like once we see the arrows in our component free body diagram, we see which arrows should get plus signs and which arrows should get minus signs. So each force vector gets a plus sign or a minus sign, depending what direction it is on a given axis. The reason I'm saying all of that very carefully, hello. The reason I'm saying all that very carefully is, therefore, the downward direction of gravity has already been taken into account when I wrote minus mg in the first Newton's second law expression. When I wrote minus mg, that was the moment that I was acknowledging that the weight of this object pulls it down. Therefore, don't also put a negative sign on the g itself. Like notice g in these problems equals the magnitude 9.8 meters per second squared, or if you like 10 meters per second squared. You don't put it doesn't equal negative. It just literally equals that number. And in the past, I've said you have to make a choice whether to make that number positive or negative depending on direction. And I still stand by that, but I'm saying now we've already made that choice. Hello. 1 second. Hello. Okay, quick. Just say hello. Hello. Welcome back. Can't wait for this. Okay, but you can't see. Okay. Just, hello.
Hey, Felix.
Hey,
Okay.
what's up?
Okay. All right. Okay.
I swear, for the last time, if he gives you homework, tell me.
Okay.
You should not be given homework.
Okay.
He gave us a test, Felix. That's worse than homework.
You are fired. I'm telling your boss.
Okay. All right. Thanks. You are my. He just told
Yes,
my
I
boss.
am your boss.
Right. Okay. All right. I'll see you upstairs.
boss.
Okay. We'll see.
You get fired.
Yes. Okay. Okay. Thanks. I do recommend having children, despite all evidence to the contrary. Oh, but I don't recommend having dogs, which he just let. Okay. Anyway, I definitely don't recommend your dogs having children. That's for sure. Unless you are prepared to buy them lots of Pokemon. Okay. So bottom line, I'm overstating it, but this happens. This really confuses people on exams. Obviously, not just being interrupted by children, but from here on in, when all these Newton's law problems. Okay, what I'm saying. Let me highlight this. I'm saying G, the number G is the number 10. It doesn't need its own not minus sign anymore. It should never have its own minus sign anymore. The minus gets taken care of when we analyze the whole force that includes the value G. I don't know if I could say it any clearer than that, but if that suddenly confused you, I am saying it's important. So if you have any questions, text me, email me, but that's the deal. G is just that number. Okay. So we got an answer for this, 20.2 meters per second squared. That was just one big sample problem. Again, you won't see that question in any of the homework things. It's a sample problem that we've just been doing live this whole time. But I think that and hopefully now that when we turn to the homework 8, which we're going to stick to for a while, like a pro tip again, if you're looking for a new homework assignment for next week, you won't find one. Just you catch up, I'll catch up. We're going to stay on this homework 8 for a while. So there's still time for you to correct it, improve it, do it, whatever, or any old homeworks that you want to improve. But what I'm trying to say is, when we now turn to homework 8, we're going to find different problems of different kinds. Some will involve friction, some won't. Some will involve angles, some won't. This put together all those elements. So hopefully we'll see the elements in separation on the homework, and they won't seem as bad now that we've seen all the elements together. That's what I'm trying to say. And that's what I'm trying to say. So let's turn to homework 8. I'm going to go out of order. Oh, it's very nice that you say he's cute. I'm looking in the chat now. You guys are very good, by the way, and I appreciate you. I know it's like you're being very polite. I know it's like distracting. Anyway, homework 8. In homework 8, I'm going out of order. And with homework 8 in particular, if we get to a point soon where if it looks like I'm about to move on from it, like next week, if I'm like, all right, I think we've seen enough of homework 8, let's move on. I invite any one of you at that moment to say, wait, but you never went over problem 2. I really want to see problem 2 or something. And then I will do it. Like in other words, I'm going to skip around. I'm going to go out of order because I know you've already seen a bunch of things in lab and things like that. Definitely. Your class definitely saw something in lab too. I also need to address. But since I know you're seeing things in interesting orders, I'm going to skip right to the problems in homework 8 where I think are the most appropriate for where we are and where I've already gotten a bunch of questions from people. So I'm going to skip but that doesn't mean, but I'm skipping. It doesn't mean I won't go back if you want me to. That's what I'm trying to say. Okay. So I will. But I'm going to start with the duck in the elevator problem because I think it emphasizes some of the issues that we're dealing with right now, and because it involves a duck. I'm not going to screen share it. I think we're okay. If I just screen share so I'm talking about problem 4 on homework 8. You've got it's a long problem that has like different scenarios. The first scenario is there's a duck in an elevator. The elevator is accelerating up and it's velocitizing up. 2 different ideas, right? But it happens to be doing both. The duck, and you're given a bunch of information. We don't necessarily need all of that information right at first, but we ultimately need all that information. But one thing to picture, like the duck is standing on a floor in an elevator. So the floor is touching the duck's feet. the elevator has some ability to go up and down or accelerate up and down. It ultimately has that ability because of some rope that's tied to it that goes over a pulley that's attached to an engine. But you see, this is an example where physics seems so complicated, but physics is actually a method for simplifying apparent complexities. What I mean by that is this. The duck is going to start accelerating. I mean, in this problem, the duck is accelerating up because the duck is in an elevator. I don't really know how elevators work. I mean, I know something about them, but I don't really understand how the engine in an elevator works. But I don't have to in order to analyze this problem. And I certainly don't think that the duck has to. Like, if you ask me the question, how does the duck accelerate up? The answer is the floor underneath the duck pushes the duck up. Like, that's what we're going to find when we analyze this problem. We're going to have to, compute the numbers and all of that. But there's a floor underneath the duck. The floor is rising. The floor is pushing the duck up. Why is the floor rising? Because there's some rope pulling the floor up. But no one is asking me here to analyze the floor. No one's asking for a free body diagram of the floor, et cetera, et cetera. So I don't care about the rope. And I certainly, therefore, don't care about the pulley that the rope is touching, and I don't care about the engine that is turning the pulley. Like, I'm being honest about this. Same thing with the sled. Like, a rope was pulling that sled. How was the rope moving? Because a child was pulling the rope. But I don't care. And similarly, if we ever analyze a car driving down a road, if you ask me what force accelerates a car down a road, my answer is friction from the ground acting on the tires of the car, because that is the only thing touching the car is the road. What's happening inside the car is a whole bunch of complicated chemistry things that I don't need to know about in order to analyze the physics. Anyway, okay, I'm getting off the topic, but what I'm trying to say is whenever you draw all these diagrams and do these system schemas, what you're trying to do is force yourself to only look at the most immediate, direct causes for the effect known as acceleration. That's what physics is sort of trying to discipline us to do, to just focus on the direct cause. Because if we allow our mind to wander to indirect or secondary causes, our mind will wander forever. Like it's, you eventually you're like, well, the grandmother of the person who made the engine, and then the grandmother's grandma, and then like next thing you know, Adam and Eve are like equaling mass times acceleration. Like, we don't want to go there. I mean, maybe we do, but not when we're trying to do a computation. Okay, anyway, so I just did. So here's the duck in the elevator. We're given the mass of the duck. We're given the acceleration of the elevator up 15 meters per second squared, and the duck, and at this moment, also the elevator at this moment, I should say, happens to be velocitizing instantaneously at 15 meters per second. So that's the situation. And the first question that we're asked for is a system schema of the duck, like treating the duck as the object of focus. So I draw a dotted circle indicating the mass of the duck, lowercase m. That's what I'm focusing on. And then the first thing I put in that picture, the first thing I put in any system schema is the center of the earth. The center of the earth is always, in every situation, it's always exerting a force on every object. So I draw the center of the earth up there, and I draw wherever I want. I tend to on purpose draw the earth up there because I'm trying to remind myself and emphasize that the system schema has nothing to do with directions. It's not about directions. It's about identifying the objects that are creating forces and therefore correctly identifying the forces. So the earth is always there, so I draw the earth. Then I do the test. After I draw the earth, I just ask myself to name any and every single object that is directly touching the duck. That's all I'm allowed to draw. That's all I'm allowed to care about. Besides planet Earth is anything that is directly touching the duck. So the only thing that's directly touching the duck is the floor. So I draw a circle indicating floor. Now here's a subtlety. Okay, so I've drawn, and that's it. That's the only objects in my system schema is planet Earth and the elevator floor. Now, one thing though, we said the rules about drawing system schemas. We said once you've drawn the circles, then you're going to connect them with lines. And our rule is for every touch, you draw a line. But then there's two exceptions to that rule that you always have to follow. One is that gravity always gets a line. Planet Earth always gets a line, even though there's no touch, because gravity is just an exception to that behavior. So you always put a line for the center of the Earth, even though there's no touch there at all. And then the other exception that I want you to be aware of and careful about is that we said whenever two rough surfaces are pressing against each other, we should be aware that generally speaking, that produces two lines, right? Just that, not ropes pulling on things, but rough surfaces pushing against each other. That generally produces two lines, because we're saying whenever rough surfaces push against each other and exert a normal force, then if they're rough, they generally also produce a frictional force along the other axis. And that is generally true. In this problem, if this problem were on an exam and you drew two lines connecting the elevator floor to the mass, I would give you full credit, because that is what I'm telling you to generally be aware of. If you have two surfaces pushing against each other, if you have two rough surfaces pushing against each other, then really the normal force will always be accompanied by a frictional force, and that means two lines. However, so I would give you credit. I just want to make this clear, because this is like a subtly confusing thing to people. If you put two lines there, I would not take off points. However, in this problem, it didn't say that the surfaces were rough. It did not say that the elevator floor was rough. It didn't provide any coefficient of friction, right? And any of the questions that's being asked and anything that's being said is all about the vertical motion of the duck. The problem didn't address or invite us to address anything about sliding or horizontal motion at all, and it never said that the surfaces were rough. So the truth of the matter is, in a problem like this, it doesn't seem like friction is going to be relevant at all. Like, it isn't, right? So if you were on an exam doing this problem and you just wrote one line for this, I would also find that totally acceptable, maybe even preferable. So there's a subtle choice. I'm not trying to confuse you. I'm just saying that the basic rule is, when in doubt, if there's two surfaces pushing against I keep saying it wrong. If you know that there's two rough surfaces pushing against each other, definitely make two lines. If you have two surfaces pushing against each other and it's really not clear that they're rough, or it's pretty clear that they're not rough, or it's pretty clear that somehow friction just isn't playing a role, you can leave off that second line. Okay, that I could say it more if you want to ask another question, but that's the clearest I can say right now. So I'm ultimately in this system schema, I'm saying the Earth is pulling the mass and the duck, and the elevator floor is pushing the duck. So the whole purpose, so that's it. That's my system schema. And the whole purpose of it was just to see how many lines it produced, so that I could then turn each one of those lines into an arrow in my pure free body diagram. Well, I have two lines, so I'm going to make two arrows. One arrow is the downward pull from planet Earth, which now in a free body diagram we call weight, which we know is always equal to m times g. So I've got the downward arrow for mg, and then I've got the upward arrow indicating the normal force being exerted by that floor. That is my free body diagram. Again, technically there could be friction in there if friction were doing anything, but if the surfaces were all rough, but I don't think they are, and I don't think it is. So that's the only forces I've got. I'm going to move on now. But notice, even there, I've got two arrows. They're going in opposite direction. That does not mean that they're equal. They don't have to be equal. In fact, I think they have to not be equal. I believe that the normal force is probably bigger than the weight pulling down on the duck. Why do I believe that? Because the duck is accelerating up. The duck is not just having its weight be supported. It's having its weight be supported and accelerated. So I'm guesstimating or predicting or whatever that the normal up is going to be bigger than the weight. Let's see. Okay. But then the question goes on to ask, okay, so it seems like it makes a left turn here in the question, but it's not really a left turn. Let me back up for one second. You see, I've got these two arrows, right? And they are opposite in direction. So many of us it's so common especially on the web. Like, again, I'm all happy for you to get as much help as you want from any website you want, Khan Academy, whatever. But on this particular subtopic, it's very easy to get confused by what people on the web say. I mean, I'm on the web. I mean, and I don't think they're saying anything wrong. I'm just saying it's very easy to get misled. You look at that picture and it's very easy to think, oh, Newton's third law. For every action, there's an equal and opposite reaction. I get, like, it's very easy to think, oh, I see what they mean by Newton's third law. Like, whenever something gets pulled down by planet Earth, I guess it must be pushed up by an equal and opposite normal force. Like, but no, that is not what Newton's third law means. And to make sure that we understand what Newton's third law means, the question now asks, oops, sorry. Like, the question asks you about Newton's third law, action-reaction pairs, because it wants to drive home the fact that those two arrows do not constitute an example of Newton's third law. How does Newton's third law work? It works like this. Each one of those arrows, each arrow and you might even want to write this down in your notes, each arrow in a free body diagram is itself an action for which there exists a reaction arrow in some other diagram we haven't drawn. Like, seriously, I'll say that one more time. Like, every arrow in a free body diagram is an action for which there exists a reaction arrow in some other diagram that we haven't drawn. Like, that is a true fact. And if you need me to say it again or write it in the chat or whatever, or watch the video again, what I'm saying is this. Let's look at the arrows one at a time. First, that downward arrow known as gravity, right? Known as weight. We analyze that. That downward arrow is saying that the Earth pulls down on the duck. I mean, that's true. The Earth is pulling down on the duck. Now, that fact alone means, by Newton's third law, that the duck is pulling up on Earth. Okay, that, I don't know if you think that's weird or not. Maybe you do think that's weird. I thought that was weird for a while, but I am saying it's true. In fact, maybe you think this is even weirder. I'm saying if the Earth pulls the duck down with a certain number of newtons, the weight of the duck, like 30 newtons, then automatically, necessarily, the duck is pulling up on the Earth with a force of exactly 30 newtons. Equal and opposite. The equal and opposite idea, the Newton's third law idea, is that every force is automatically a symmetric two-way interaction. The Earth cannot pull down on the duck without the duck pulling up on the Earth. It's like a perspective thing. It doesn't matter whether you look at it from the point of view of the duck or the point of view of the Earth. The Earth and duck are in a tug of war. In fact, that's partly what the system schema is trying to connote by just drawing two circles with a line between it. It's trying to get across, this is a symmetric thing. This is just an interaction between two objects. There's no special direction for this. Again, it is like to say otherwise, there's no way. Sorry, what I'm saying is, I married my wife on October 20th. Obviously, my wife married me on October 20th. It would be ludicrous for me to say that I married her, but she didn't marry me. I mean, maybe that she'd want to say that, but right? Forces are like that. It's just an interaction. It goes both ways. So if the duck is pulling up, if the Earth is pulling down on the duck, then necessarily what Newton's third law is saying is the duck is pulling up on Earth. So that's the action-reaction pair. And notice how it's phrased. The action has two objects in it, Earth and duck, and it has a word, pull, in it, and it has a direction, down. The reaction has the exact same two objects, Earth and duck. It has the same word, pull, and it just has the opposite direction, up. That is an action-reaction pair. And that, I'm yelling a lot. Oh, we still have 11 minutes. Okay. I mean, but seriously, people, this is one of the most misunderstood laws, really. I mean, in all of, it's very easily misunderstood, so I'm yelling about it. It's also very interesting when it's correctly understood. That action-reaction pair that I just described the action-reaction pair of gravity, that the Earth pulls down on the duck, therefore the duck pulls up on the Earth. And by the way, it's not even a therefore. It's not like one happens first. I mean, they happen at the same time. Anyway, that action-reaction pair would be happening even if the duck were just in free fall. Like I'm saying, there's an even number of forces in the universe automatically, necessarily. Even if there's only one force acting on the duck and nothing's supporting the duck and the duck's just falling down, then the Earth is pulling down on the duck, but still, the duck is pulling up on the Earth. That's it. Where is that arrow drawn? It would be drawn in a free body diagram of the Earth, which nobody asked us to draw here. But you see what I'm saying? The downward action in our free body diagram has an upward reaction in the diagram of the Earth, which we just happen not to have drawn. That's the way Newton's third law always is. It's always about two objects. I push you, you push me back. So to move on, then similarly, the other arrow that happens to be in this diagram, the normal force, what that means, that didn't have to be there. A duck could have been in free fall. There's no law that says that when you're pulled down, you've got to also be pushed up. If that were a law, nothing would ever accelerate, right? But it happens to be the case that this duck is being supported by a floor. So the floor is pushing up on the duck. So pair number 2 here at the bottom of the page, pair number 2, it says, pair number 2 describes the normal force. The floor pushes up on the duck, and therefore the duck pushes down on the floor. That pair has nothing to do with Earth, just like the other pair has nothing to do with the floor. I mean, I cannot emphasize this enough. I've already emphasized it too much in a way for today, right? I'm sure you either get it or you don't, right? But so those are the action-reaction pairs. For every arrow in a diagram, if we were back on the sled problem that we've been doing for a week, if I asked for all the action-reaction pairs from that diagram, there'd be 4 of them because there's 4 arrows in the diagram, right? So a diagram that has 4 arrows in it actually means that there's 8 forces happening somewhere in the universe. All of this is trying to emphasize that any arrows that you ever draw in a diagram are not action-reaction pairs. What we're really trying to get across here is when you start drawing arrows in a diagram, don't think that every time you draw an arrow going one way, you've got to have an arrow balancing it going the other way. That is a common and huge misconception. Newton's third law is not talking about 2 arrows in one diagram. It's talking about arrows in 2 different diagrams. Any 2 arrows in a diagram are definitely both actions. That's all I could say about that. So now moving on in the problem, it then asks the key question really here: what is the magnitude of the normal force pushing up on the duck? Okay, and again, it's asking this because we're just trying to get, because a lot of times people will just automatically think that they'll think they memorize some formula that the normal force equals the weight, or people remember that or think they remember that from high school or something. There's no formula for the normal force. The normal force is whatever it needs to be to obey the law, Newton's second law of motion. So in order to figure out what the normal force is, we do the same thing we did in the sled problem. We just look to the axis where the normal force is acting, and we apply Newton's second law. So in principle, what we'd have to do here, we were asked to draw a pure free body diagram. In principle, we would now have to choose axes and divide up those vectors into component vectors, but they already are. Thank goodness we happen to have a simpler situation here where all arrows are already pointing along a given axis, so we don't have to break anything up or do anything. We don't have to do any trigonometry. We already have components here because it's a simpler problem. So we just go straight to the y-axis and we apply Newton's second law. We say the sum of all the y forces equals mass times the acceleration along the y-axis. So I just copy right off the picture. I had n going up, I had mg going down. So I say n minus mg equals ma sub y, just like we did in the sled problem. Only hopefully now, hopefully it seems a little bit like less overwhelming. But notice here, no one said the acceleration along the y-axis is 0. no one said here that these forces are balanced. No one said that the duck is not accelerating. In fact, they said the duck is accelerating. The problem says that the duck is accelerating up at some non-zero rate. So what does the normal force equal? It equals mg plus may, and nothing cancels out. What does that mean in English? It means the normal force has to, yes, support the weight of the duck, but it has to do even more than that. It has to support the weight of the duck plus push it hard enough that the duck goes up. That's what that's saying, right? That's why the duck is going up, because the normal force underneath it is stronger, or is more newtons than its own weight. Yeah, that's what that says. So note, N does more than support the duck's weight. It accelerates the duck up. That's what that says there in the axe murderer handwriting. So if we're solving for the normal force, we just plug in the numbers now. So N equals mg plus ma sub y. Again, by mg, we mean the weight. By g, we mean that number 9.8, which I tend to round to 10. We don't put in any minus. This is like what I was yelling about 5 minutes ago after Felix came in. Like we've already, even though now mg is positive, that's okay. Like, just because we rearranged the equation. Like, we acknowledged the downward direction of mg at the moment that we acknowledged the direction of every single force. When we took our diagram seriously and we translated our diagram into an F net equals MA statement, that's when all directions got acknowledged. So we don't want to double count or double back on ourselves. So G is a positive number here. I mean, I can't, so I just plugged in 18 times 10 plus 18 times 15 is 180 plus 270. So I get the normal force equals 450 newtons. That means the floor is pushing up a lot harder than, I mean, the duck only weighs 180 newtons, but the floor is pushing up at 450 newtons. And then the question asks, how far does the duck go in 7 seconds from the perspective of the ground? And this is the one place where the velocity comes into effect. Now, the velocity is not constant, right? It's the velocity at that moment. The elevator is accelerating, so the velocity is continuing to increase. But we have an equation to take care of all of that. We want to know how far a duck accelerating at this rate with an initial velocity of this goes in 7 seconds. So we plug in our old equation, and we get that the duck would move up 717.5 meters. And this last little exercise there is an illustration of, or a reminder of, why we're doing all of this stuff in the first place. The whole program here is at the first half of the course, we learned that in the beginning of the course, we learned the whole point of physics is to predict where something is going to be when, right? It's all about how things move through space and time, predicting the location of an object at a given time. We found out in the first half of the course that the way to do that is to know an object's acceleration. That if you know acceleration, you can predict where things are going to be when. So now in the second half of the course, we're finding out, well, where does acceleration come from? How do you know acceleration? What causes acceleration? And the answer is forces. So we do all of these diagrams and all of these forces, and ultimately to get the acceleration, so that we can use that acceleration knowledge to tie back to whatever we learned at the beginning of the course and continue to answer the fundamental physics question, which is, where is something going to be when? And that is it. So we're actually ending like 45 seconds early for a change, which is amazing. So I will stop. Again, I will hang out for any questions at all, but if other than that, or to turn back the pages for the notes or whatever. But yes, right. Thank you, Melita. Okay, so have a great day. I mean, I'm turning off the recording. You please have a great day, great weekend. Don't do any new homework. Just catch up and be patient with me. And yes, but I'll be here to answer questions when I turn off the recording. Bye. Okay, bye, guys. Wait, what's the answer to quiz?